Everybody, and welcome back to the first session on Tuesday morning. There is just a slight change of program. The third paper has been cancelled, which means that we are going to move forward the last two papers of the first session. So let me start by introducing the first speaker today, who is Bob Behringer from Duke University, North Carolina. And Bob is going to speak about statistics of dense granular material.
Good morning. I hope can everyone hear me? Great. So actually, let me just begin by thanking the organizers for a very stimulating meeting and to organizing some sunshine. So, before I get started, I really need to recognize actually a fair number of people who are either been junior people working on this or with whom I've collaborated, and also places that have provided the funding for this. So what I'd like to do is basically, having trouble with hearing me? I'll try to talk a little louder. So let me just sort of go through a quick roadmap. So I'd like to raise a couple of questions and issues. Some of this will be, old hat to a number of you others. It might be a different perspective.
Oh, just turn the microphone
Better on.
on the top.
Okay, does that help? Okay, all right, very good. Okay, so then what I'd like to do with most of the time that I have is to look at experiments which then explore a number of different concepts which I will read off to you. Good. So in particular, of course, there are many questions you might ask about granular materials, particularly dense granular materials. And the ones I want to look at today are the ones which are outlined in red. In particular, what are the statistical properties of granular material? So my point of view is if you really want to understand granular materials, then you need to look at their fluctuating properties as well as their mean properties. Then, in addition, then you can ask questions about, well, what happens when you make the transition from a fluid-like to a rigid system? Then the last topic I'd like to look at is how can we understand granular friction? So here's my quick assessment of the state of theory, which is that vis-a-vis granular gases, I'd say the theoretical modeling is pretty solid. I mean, there are surely open questions, but if you then compare to the situation for dense granular states, which are presumably what we're here to talk about, then I'd say questions are much more open and unsettled. Again, I want to focus on statistical questions, like how do you understand fluctuations and disorders? How do you understand what are the relevant lengths and timescales in the system, for instance? Okay, so if you then look in a little more detail at the smaller scale structure of these granular systems in dense, slowly moving states, you're immediately struck by several very simple phenomena. Namely, what you find is that forces are carried typically inhomogeneously, and so then the jargon is force chains, but force network might be a little better way of describing that. In addition, I'm going to talk, unlike some theorists, I'm going to talk about real granular materials which have friction, and that actually almost enforces on you the idea that there'll be history dependence and other things which make the system, in principle, complicated. And in addition, when you start to deform the system, you inevitably break the force network, and that will lead to relatively long-range spatiotemporal fluctuations. So I'm going to keep hammering on you. You can debate this with me later, but I want to really, from my point of view, I really want to emphasize the fact that a statistical approach is a particularly sensible way of going about understanding these systems. Okay, so now we're going we're going to, of course, look at static states of the systems, but then you can also ask what happens when you push a system around. Is it elastic, a granular system? Does it have other properties? I mentioned jamming before, so as you actually condense a granular material in from a fluid-like density, then it will become rigid. It will have non-zero elastic moduli. In systems which are isotropic, then density is implicated as the major control factor, at least for simple systems, spherical particles and so forth, which, okay, so poor industry guys maybe think that's sort of irrelevant, but that's a starting place to try to understand these kinds of systems. If you then push the system much further, then you get irreversible or plastic deformation. Let me just point out a couple of ways of typically generating plastic deformation, which is, say, by shear. And I'm going to talk later about simple shear, and also we'll look at something I'll call pure shear. And so let me just sort of raise the issue right now. When I say pure shear, I'm going to squeeze in one direction and dilate in the other, but keep the area constant. When I do simple shear, I'm going to, what I call simple shear, and I'm not sure there's always a unanimity of definition. I'm actually imagining that I'm pushing and pulling on parallel surfaces, but in the opposite direction. Okay, so at any rate, I want to focus on fluctuations, force networks, etc. And so then, here's an example, right, which shows the presence of these force chain or force network structures. This is physical data, right? It's taken from a co-ed experiment, and I'll actually show you a sort of a close-up of the actual experiment. But in this, do we have a pointer by the way? The old-fashioned type. Battery doesn't wear out. Okay, so in this system, what's actually happening is we're shearing on the inner surface of a flat system consisting of photoelastic particles, and I'll tell you a little bit more about how that works. But for the present purposes, where you see bright, or where you see red rather, is where the forces are large, and where you see blue, then the forces are quite low. And as the system evolves in time, as it's steadily sheared, the location and nature of those force chains fluctuates. Now, you might say that's an artificial experiment, it's 2D, but if you look in a 3D setting, and so this is a channel of real granular particles that were being sheared, and then look at the pressure in some place in the system as a function of time, you'll see a signature of the forming and breaking of these structures in the force or pressure fluctuation. So this is from an experiment, again, where we sheared spherical glass particles. And you might notice that the mean pressure that we measure is down here, but if you look on fast time scales, even averaging over, say 100 particles contacting the detector, you see strong fluctuations. Okay, so now hopefully Mr. Gates will help out. Okay, so this is actually a close-up of that experiment that corresponds to the blue and red picture, and now you can, all goes well. Okay, so now you can see here's the shearing wheel. The particles are being dragged along by that at the inner surface, and then you can see, I think, fairly clearly these force structures that build up, but then evolve and eventually break. And the little black marks, by the way, are little markers we put on for tracking the particles. So, good. Let me also show in a different setting, a somewhat faster flow, where these structures also appear. And this is, if you like, a little bit of a warm-up for Roger Place's presentation later this afternoon. These are also the same kind of photoelastic particles. They're in a kind of Hopper geometry, and the particles are going to be flowing out here. But I think this also gives you a flavor that they appear in a lot of different settings. That is the force chains. So you pull the plug on this, and actually what you also see is that the flow is not particularly uniform, by the way. Okay, you can see that it's jerky. There really are velocity correlations in this system, and at the end, the system actually jams. It's actually not a permanent jam, but it has a nice little arch of particles which are carrying the force, and that's what's clogging the outlet at the end of that flow. Okay, that's high speed, by the way, just in case you thought that was something you could see with your eyes. Okay, so friction, right? So this is always the exercise from hell to give to your undergraduate students, right? Okay, so you're teaching mechanics in the first semester, and you say, okay, well, I'll give you a block sitting in a corner. Okay, what are the forces on that block if it's a frictional block? The answer is you don't know. Okay, so if you tell them to give you an answer, they'll probably give you an answer because they have to, right? But in actual fact, if I slide the block down this way, I'll mobilize friction up the plane. And so when I've finished, I'll have a frictional force up here and then normal forces, but no frictional force up there. But I could have slid the block down on that surface, and then I would have reversed the planes on which there were friction. Okay, so inevitably there is an effect of history dependence and, if you like, unknown and therefore randomness in real frictional granular materials. Okay, so what I like to do is pull in tools that are commonplace in statistical physics and not necessarily always used in other disciplines. And so we'll look at distributions of things like forces. We'll also look at correlation functions and other kinds of structural or related information. So some of these tools are common in disciplines besides physics, and some are not. And so I'll try to make them clear where I use them. Okay, so enough for introduction. And let me start now talking about some specific experiments. And in particular, since I'm beating you over the head about fluctuations, let me show you experiments where we directly measure forces and their distributions. Okay. So the actual experiment consists actually of a flat sheet of these particles, and they're confined by a pair of walls which we can then push in or pull out under high control. So we can prepare any given strain state that we like. Now, because the particles are photoelastic, they respond when they are pushed on. And so if you actually zoom in on a particular particle in this system, then what you'll see is inside the particle, you'll see a bunch of light and dark bands. Okay, so those bands actually encode the forces on the particle. Right? If you actually then compress the system of these particles, so squeeze in equally on all sides, you get a state that looks like this. Okay, so again, lighter sort of implies that there's more force on a particle, and dark means lower force. But if I do my so-called pure shear, so I squeeze this way and expand equally that way to keep the area fixed, then I generate a different kind of structure of so-called force chains or force network in that system. And so I want to actually emphasize early on that there is indications that there's really a difference in the statistics of those two different states. Okay, so again, you're looking at the particles through cross polarizers. So the arrangement is that you have a sample. In our case, these samples are horizontal, but okay, bear with me. Okay, and then you use crossed circular polarizers, and so then when you squeeze on the particle, okay, it's birefringent under strain or photoelastic. So again, that means that you induce differences in the index of refraction, which are sensitive to that to the applied stresses, and that's what we're going to use. Okay, so again, the logic here is, okay, if I knew the forces acting on the particle, that's what I want to actually determine at the end, because I can compare that to theory. If I knew the forces, then I would know the stresses inside the particle, and then if I knew the stresses inside the particle, then there's 19th century physics that was discovered by Brewster that tells me what the photoelastic response is. And in fact, the photoelastic response that I get depends on the difference in principal stresses at a given point, a ray going through along the axis of the disk, okay, and then a bunch of other parameters, but it appears as a sine square. So it's a nonlinear inverse problem, but you can solve that problem, okay? We do an iterative solution, and so then we do the reverse. We take the photoelastic image, and we use, in the end, the contact forces as fitting parameters, which we then solve from just by standard numerical techniques. But the deal is we have to do it on large samples, so we're talking about a couple thousand particles, which is actually getting to be pretty reasonable. So over time, we've got a pretty efficient code for that now. So these are actually comparison images where we took photoelastic images from the experiment. We then carried out our inverse procedure to give the contact forces, and then asked how similar would the image be if we took those contact forces. And actually, so this is an experiment and a fit. Experiment and fit, it's actually pretty reasonable, and we actually do somewhat better than these now. Okay. And we also actually use images which have a lot more particles. So this is about 3,000 particles. Okay. So now, what about theory? Okay. Well, let me build up to that, but let me first show you that some experimental data which distinguish whether you have isotropically compressed your system or whether you've sheared it. And so because we're measuring vector forces, we will distinguish distributions of contact forces depending on whether it's the frictional force, the tangential force, or the normal force. Okay? And so it turns out that no matter whether you've prepared your system by shear or by compression, that the frictional forces always have a very nice, clean exponential distribution. Right? So this is a log scale, linear scale. So exponential is a straight line. On the other hand, if you contrast the normal force distributions for shear and compression, there's clearly a difference. Okay? And at least heuristically, well, that's more or less exponential in the tail, and that's clearly not. Maybe quasi-Gaussian. Okay. So now, what is the theory out there? And the theory actually is contained in basically Edwards entropy inspired models. So the idea behind this might go something like this. I will simply imagine that I create some ensemble of particles, and then I want to find all the possible force combinations that will be consistent with the geometry of my packet. Okay, so that's the spirit of that. So you simply generate all members of a forced balance ensemble, and force and torque in principle, and then you look at the distribution of contact forces that come out of that. Okay, so there's a longer story about Edwards entropy, and I don't know that even though we're in the home of Sam Edwards, I'm not sure there's anyone who will defend him, but I'm going to skip over that a bit. But basically, it's the idea that in a very quick sentence or two is that for granular materials where you don't have energy as a conservation principle, you revert to what is conserved. In our case, it's the stresses which are conserved, and use that to construct an ensemble. So that's the spirit of these things. And so now there's been work, again, computing these force distributions by the group at Leiden, and also by people at Duke, Josh Sokol, Brian Kai, and others. So if we now compare, these are force distributions, contact forces, for an isotropic distribution, and now for a system where the stresses are becoming increasingly anisotropic, stronger and stronger shear. And so you get something which has this sort of Gaussian-like tail in the isotropic case, but no matter whose brand you pick, you tend to push towards an exponential as you increase the force anisotropy. Okay. Well, okay, so now there might be a little bit more to this, and so let me, at the risk of making a little seasick, let me go back to maybe an earlier picture. Yeah. So, and this picture and that picture heuristically do not look the same. Right? So it looks, in fact, like you can follow force chains over a relatively long distance here, whereas it's very hard to imagine that you can find a sort of coherent force path through the isotropic state. And so one way to try to look at that is by looking at a force correlation. So a general correlation function says I'll take some quantity of interest and I'll look at an average over r prime of values at r plus r prime and r prime. Okay, now we're going to change this a little bit because usually you also average over all angles. But we're not going to average over all angles because angular information is really important here. So we're going to simply keep the angle fixed but average over all distances of comparable size when we look at the forces. And so now when we look at the sheared system, then the correlation function, and this is log-log, okay, is clearly much stronger along the chain direction than along the transverse, whereas in the compression direction, you actually have rather short-range correlations, which don't care about what direction you look. All right, good. All right, so I'm going to make a quick switch on you. Okay, just when you thought you were getting comfortable. Maybe. Okay, and so let me talk about a different sort of phenomenon, namely this transition that you might have between a fluid-like and a dense state, a solid-like state. And so now this actually harkens back to work which was a proposal, if you like, by Andrea Liu and Sid Nagel over 10 years ago. And the idea is that they wanted to try to unify a whole collection of disordered particulate-like systems. And so there's maybe most of the members of that class. But the idea is that you can imagine that I looked at a real molecular glass. And I said, well, look, that molecular glass has an analogy vis-a-vis jamming and complex behavior near jamming that's glassy-like. Okay, so granular materials and molecular systems might really be this sort of the same members of a different class, except granular systems don't have a temperature. So nevertheless, you have a phase diagram for where if you cool a molecular system, it becomes glassy and then jammed. If you have a granular material and I compact it, it develops non-zero elastic moduli and so forth. But all these systems I can cause to flow if I shear them strongly. Okay. So that particular idea was then developed much more by, okay, do I have them up here? So Ahern, Silbert, Liu, and Nagel. And specifically, they looked at simulations of spherical particles and near an isotropic jamming point. The predictions then are the following, that as you go up in packing fraction phi, there will be a point at which the mean contact number will jump from 0 to a non-zero value, which depends on what it takes to produce a rigid state in your system. So that's the number of contacts, which will be 3 in principle for frictional particles and 4 for slippery particles, frictionless particles in 2D. And then as you increase the packing fraction above that critical value, that Z will grow as a power law with an exponent of about half. And likewise, above the critical packing fraction, the pressure will grow as a power law, and the exponent there depends on the interaction force between your particles. Okay, so that's one set of predictions. And then another one of these new ensemble predictions, this by Silke Henkes and Mubal Chakraborty, claims that there will be a well-defined relation between the pressure and the contact number, which we can also test. Okay, so we go back now to our photoelastic system and our little squeezer device, and we're looking at isotropic systems, and we're going in and we're now measuring the forces of the contacts, and we're measuring whether the number of contacts, and from that we can then get all quantities of interest, including pressure, and of course the average contact number. So now if you look at so that's a Z, not an M. So if you look as a function of phi, in these experiments, what you see, depending on whether you count rattlers or not, you see that there's a relatively sharp rise in the mean contact number that you measure. And then if you zoom in on a finer scale, then above some value which we think is the jamming transition value, you find a power law increase in Z, which is consistent with an exponent of a half. And likewise, if you go looking at the pressure, okay, again, we can compute the pressure because we know the contact forces, then you find that the pressure also has a scaling behavior, and the exponent, again, is consistent with the force law that we actually measure for our particles. Okay, so it's a somewhat longer story. And then lastly, the red line is the Henkes-Chakraborty prediction. Oh, that should be Henkes, sorry. Henkes-Chakraborty prediction is the red line for P versus Z, and in fact, the data are quite consistent with that. Okay, so let's see how we're doing. So let me now jump into a different domain. Okay, and again, I want the theme here, okay, even though the subject keeps shifting a bit, is always to be looking at the statistical properties. And then now I'd like to look at what happens if we generate large deformations in our system, okay, in this case from shear. Okay. So now we're going to go back, first of all, and look at our biaxial system, okay, and we're now going to apply pure shear to the system. So we're going to squeeze one way, dilate the other, and keep the area fixed. And we're actually going to track, photoelastic information. We're also going to track positional and rotational information. And so we've changed the procedure a little bit. We mark our particles with fluorescent dye now. And then when what that does is it means that the dye doesn't interfere with the photoelastic measurement. But when you want to see where the bar is, you just illuminate with UV light, and then you can see the bar. So we're taking multiple images as we go, but we're doing this this is snail's pace physics. So you make a small deformation, make your measurements, take another deformation, and then over time you build up a big shear strain. Okay, so again, this is the kind of system to give you a feel. So the photoelastic image looks like this. And you take off the polarizers, in fact, of course, you realize how much information the photoelasticity is telling you. Okay, so let me just show you what this looks like. And now, let me make what I think is really important here, perhaps something that people haven't thought so much about. This system starts off at a packing fraction below jamming. There are no stresses in the system when we start. We're not going to change the packing fraction, but we are going to squeeze the system unequally, okay, to produce pure shear. And what you'll see is this will generate a jam state. So this is just a video of time-lapsed, a time-lapse video of what that looks like. Okay. So as we shear that system, we produce a jam state. Okay. So as soon as you change the system from being isotropic to anisotropic, the standard rules, at least in some communities, that the only thing that matters is the density. That clearly can't be right. So let me run that by you one more time. So all we're doing is shearing it. We're not changing the density. And then, by the way, so if you do the other way, so now we reverse the shear. So
Pure shear?
this is pure shear. Okay. Then actually what you do, of course, is you build up a network in the opposite direction. And so in doing so, you melt away the original network to the point where the stress becomes very small. And then you build up a force network in the perpendicular direction. Okay. And actually in the interest of time, I'm going to skip over what the rotation looks like. But these systems actually don't remain homogeneous. You develop shear bands in them, and so this is actually this is the displacement field between two small incremental steps, and for various values of the shear strain. So you have a region, by the way. So the particles are moving en bloc in two opposing triangles, and then all the slip tends to be isolated in the middle shear band. Okay. So the parting message I'd like to leave here is the following. If you look at pressure sort of as a function of strain, or if you look at contact number as a function of strain, so black is in the forward direction, red is in the reverse. Okay, that's a highly hysteretic phenomenon. But the curious thing, which is just an empirical observation, is if I now look at the pressure versus contact number, then in fact the pressure versus Z collapses onto a universal curve. Okay. All right. So let me look at a different aspect of this shearing process, namely the shear band. And I'd like to do that in a slightly different context. So I'll go back to the Couette geometry that I used as an example of force chains at the beginning. So now we're looking at a system, again, where we're shearing these photoelastic particles. And we're going to look now in the region near that shearing wheel. And in that region, okay, that's what the experiment looks like, right? It's actually a lot of particles. Okay, it's 50,000, 45,000 particles. So in the region next to the moving wheel is where all the action takes place. Okay, all the motion at least. Okay, and so you get a velocity profile which looks something like this, right? So that's where the wheel is, and as you move deeper away into the sample, then that velocity profile decays roughly exponentially, right? So it never goes away, as far as we can tell. Okay, it just takes a lot of patience to actually see the motion as you move away. Okay, so now what does that motion look like, and can we understand it in terms of any simple-minded phenomena? And in particular, the particles are being pulled over themselves and so forth, and so there are really three pieces that you might think of as being present in that motion. So there's very obviously the mean azimuthal profile. Okay, so that hits you immediately. But in addition, you're locally deforming particles, and you could think of part of that motion as being just like elastic deformation. Okay, but then particles actually move past each other irreversibly. Okay, and that is a diffusional type motion or a plastic motion. And so what I like to do is focus in particular on the diffusion and also in principle on this small scale elastic piece. So the way, actually, go this way. So the way you would track diffusion in an ordinary system, right? By looking in a molecular system and tracking particles, I would look at the variance of a particle trajectory, right? And I average over that. And if I had a simple Brownian system, then the variance of, say, the x coordinate of a displacement would grow linearly in time. Okay? That's how you would measure diffusion in principle in a molecular system, if you could go in and look at particles. Okay? So, in fact, if you take a picture, sort of a random walk picture, then you show that actually corresponds to a diffusive light equation. All right, so if you take such an approach and simply look at where particles are going, you discover that the mean, that the variances, if you like, don't grow linearly in time. Okay? If you're looking along the tangential direction, then they seem to grow faster than linearly, which is so-called superdiffusive. If I look in the radial direction, they seem to be going slower, except that they come in with some finite slope. Okay, so now the question is that really some exotic diffusive behavior, or is it something else? And so one suggestion is that it's exotic behavior. And so if you have, say, correlated motion, okay, then in fact the exponent won't be a half, but it'll be bigger than a half. And if you have anti-correlations, then the exponent will be less than a half. So you might think it's that. Okay? But there's something else hanging around the wings, which is if I have a mean flow in my system, in particular shear flow, then in fact the motion doesn't have to be simply diffusive. Okay, you have what's called Taylor dispersion, okay, and that means that the variances no longer have to increase linearly in time. And so if you have very simple shear flow, you can do a computation of how those variances might behave. But we don't have a simple shear flow, right? We've got some horrible exponential-like profile. But it doesn't mean that you can't try to create a simple model that has the right kind of flow profile. So if you simply say I've got a random walk model in the presence of an exponential velocity field, then I can write down a simple time-stepping model with zero adjustable parameters and check to see if I get the right kind of variances in my system. So here's my original experimental data for now radial and tangential variances. And so now this is sort of a slightly ironic situation, but the model is the noisier data in this case, okay? But it actually tracks rather well the experimental data, which is the less noisy data. So it looks to us like we have normal diffusion in a complex flow. Okay, so since my time is short, I'm going to actually jump to one last point in shear flow rather than explore this Couette system a little bit. So if anybody wants to talk to me a little bit more about diffusion in the shear band, I'd be glad to do that. But I'd like to look as the last issue, last subject, at what what friction looks like in a sort of a stick-slip configuration. So obviously, we wouldn't be the way we are if we didn't have friction. Okay, those of you who skated in on the ice know that. So now we'd like to sort of zoom in on what you mean by granular friction. And so that we're going to actually again exploit photoelastic particles, but we're going to do it in a slightly more, complicated geometry. So we're going to have a channel of particles which is vertically oriented, and we're just going to pull a rough object across. And we're going to pull through a spring so that will give us stick-slip behavior. Okay? But at the same time, we're going to look at what's happening to the force structures in our granular system by carrying along a little camera with us so that we can see the details correlated with the pulling force, so the details of the particle structure and the pulling force at the same time. So this is a slightly peculiar picture. So this is looking end-on into that channel of particles, and this is more of a side view, and you can see the camera is here. Okay, so that's the point. Okay, again, we're using photoelasticity, and so now as you're pulling along, you see these characteristic shear structures, and this is more like simple shear, right? And so what's happening now is simple shear has its compressive direction oriented diagonally at roughly 45 degrees. Okay, but again, let me just sort of give you a flavor of what this looks like, which is maybe the most fun. And maybe if you remember what it looks like, that might be the most important thing. So this is a split image. This is the pulling force synchronized now with the image of the photoelastic particles, and this is the object we're pulling across. It's dark for obvious reasons. Okay, so now as we move along, the actual pulling force will darken. Okay, so, but now this is sort of if you like, a warning sign. There's going to be a little bit of a slip event here where the pulling force drops. Okay, and so, so now watch down here. Okay, so you have now a failure event in which that force network breaks in some places, not others. Okay, and I'll run it up to here where you have, this is a magnitude 7. This is done for Charlie Campbell's benefit. Okay. Who lives in Los Angeles? Okay. All right. So we're coming up now on a big event. And so you see a gradual evolution of the network, but very little, some small adjustments, which is sort of creep-like behavior. You're getting up to the tip. Okay. And bam. Okay. All right. So now, okay, so I'm really running short of time. But it's clear you have stick-slip behavior. When the system slips, your force drops, and the energy stored in the system also drops. And so you can then try to relate that to a Gutenberg-Richter type law. And in fact, you get, if you now look at and Mr. Gates sort of failed me here, but if you look at a PDF of the energy drops as a function of the size of the drop, you get something which is a Gutenberg-Richter-like law of the exponent is a little lower than the standard Gutenberg-Richter exponent. Let me just leave you with one last idea about this, which is that in some sense, there are parts of the system which are really quite dull and simple. If you look at the maximum force at which the slider starts to slip, and you look at the force, so that would be the red, the blue dots and the red fit. Or if you look at the point where the slider comes to rest again, which is the yellow curve and the green dots, those are just Gaussian-like structures. Okay? There's nothing, in spite of the fact you get a Gutenberg-Richter-like behavior, there's nothing exciting in that. Okay? In fact, what is exciting is that when the system starts to slip, when you break a force chain, if you like, then you have to support that force with other force chains. And that's when the behavior can become complex, and you can have multiple failures, so you get a cascade of failures, and that's what gives you the Gutenberg-Richter. So again, you can put that into a model if you like, but maybe there's not time to talk about that now. So let me just sort of draw some general conclusions, which is, maybe first and foremost, I want to hammer home what I believe is taking a statistical approach will give you an awful lot of information that you might not get, if you simply look at average behavior. So I think there's an awful lot to be learned from that. And then in more detail, right, we've seen that you can get agreement with some of these generalized Edwards-like ensembles for the contact force distributions. But there's really a difference between sheared and isotropic systems, stress isotropic systems, and that has come out in several different settings. When we look at diffusion in, say, sheared systems, that diffusion looks to be simple Brownian, but in the presence of a complex swell. Okay, so that's probably as much as I should say. Good, thank you. Yes?
Quick comment. You can actually measure diffusion.
Can you speak up a bit?
Yeah.
You can,
I'll repeat the question.
you can actually measure diffusion by taking the affine displacement, subtracting out the mean flow shear displacement.
Right.
So for simple shear flow, it works very well.
Right. So the comment was that you can actually take you subtract out affine motion from the flow and look at the non-affine part, and that works well. And in fact, that's something I skipped. So we actually do that, and you can actually get exactly the diffusive behavior by looking at the non-affine part. Yeah. So if you like, I can talk to you a little bit later about that.
The general question was that you seem to emphasize the history dependence.
Right.
Doesn't that mean that you're missing some relevant variable in the system?
Well, so the history dependence means that you want to know, if you like, you want to know what the tangential forces are. That you can't ignore the tangential forces in this system. Okay, so we do get that, in principle we do get that information. Okay, so I guess what I really want to argue is that if you have history dependence, then in general, if you do an experiment multiple times, you cannot expect that you will regenerate exactly the same thing if you have slightly different initial conditions. So that's more the thrust of that argument. Okay, we'll go from that side to this side.
Okay.
Thomas.
Yeah, I need two fingers to know you're pointing at me.
Okay.
I'm a little confused about something, so maybe, and I'm not being ironic. Maybe you can straighten me out.
Okay.
When you look at the O'Hearn-Nagel type theories of the jamming transition,
Right.
typically those theories and the numerics that support them are based on frictionless particles.
Absolutely.
However, your experiments, I should imagine, are not based on frictionless
That's
particles.
right. Yep.
And so, shouldn't we be surprised, or rather, not just appreciative of their cleverness in getting it right, but actually surprised that there seems to be something quite new here in the fact that frictional results seem to matter?
No, I think that's an excellent point. And so there are. So let me just say, two things. One is I agree with you. We should be surprised because there is friction, and that system, a frictional system, doesn't have to be like the frictionless one. The thing which I think probably saves the day is that if you look at the typical size of the frictional force relative to the normal force, the friction is down by an order of magnitude from the normal force. I suspect that that's what saves the day. But you can imagine, of course, going to really, if you go to particles which are interlocking, for instance, and that probably would not be something you could match over.
If I could just ask a follow-up question. Alternatively, you could prepare the system in a non-compressional way, which might more fully activate the frictional forces, and then you would imagine that you would probably start to see a different kind of behavior.
Right. No, I think that's right. So depending on preparation history, you can, and in fact you do, you find there's some differences in what you get for the jamming statistics. Yep.
I think probably we can't take any other questions.
Okay, I'll talk to you.
Sorry. Thank you.